Hello everybody, I'm Zap Andersson from Autodesk. Today I'm going to demonstrate a bunch of the OSL stuff more in depth. Now be warned, this will be long, it will be pretty much unedited, and I will probably do a bunch of mistakes and things, so bear with me. This is trying to make this as informative as I possibly can. I set up a scene here with some box and some teapots, which, yeah, just to have something to look at. And I have a physical material set up. So everything is done through this physical material. I would like to say this is the recommended workflow. Always use the physical material and plug your OSL shaders into it. And we're going to walk through, not every one, because there's 101 of them, but a fairly large set of the OSL shaders to see what you can do with them. We're kind of going to start in this, like, the basic category, and we're going to try a couple of things. Like, for instance, we have a checkerboard shader. Okay, it's not terribly complicated. It does exactly what you expect it to. It makes a checkerboard. What else can you say about the checkerboard shader? Well, you can say a couple of things. For instance, people have asked me, so what about the viewport for OSL? Well, actually, if you go to your material and tell it to show up in viewport, you see that you actually do get something in the viewport, and it looks quite decent. However, it should be I would like to underline that anything that shows up in the viewport is a 2D baking of the OSL. So it's basically doing this. It's doing a render this, and this is used by the viewport code as a texture in the viewport. In this particular case, it works fine because the checker is simple and it's mapped in UV space. So there's no problem. But if I try something like the candy shader, which does kind of random dots, you will see that yes, there's dots here, but it doesn't match, because this simply got the 2D baking of this, or well, a version thereof, as its what it maps to the object. So you kinda see what it looks like, but it's not exactly the way it looks. We can take another example, even more obvious. If we take the noise and we connect that, we see that this is a 3-dimensional noise, and it can look deceivingly similar, but it kind of gets obvious here on the side that it's all squished and there's no continuity over the edge and everything. So just be aware that any viewport stuff is a pure 2D baking. It's a cheat. It's a let's make something better than nothing kind of thing, and it's nothing more complex than that is supported yet. So let's turn the viewport stuff off for the moment, because it will probably just confuse us. If we go back to our checkerboard, we notice a couple of things. First of all, it has a UVW input, which is where the UV coordinates go. But wait a minute, I haven't connected anything, so why is it working? Well, a very important special feature in OSL is that a shader can have what we call a computed default. If we look in the source code, as you know we can do, we see that the UVW has a default which is an expression. It takes the default U and V coordinates and uses that. So if nothing is connected, it will pick a default U and V value. The default U and V value in max is set up to be the first UV coordinate. So without doing anything, it's mapped to the first UV coordinate. And the thing is, with things that have a computed default, this makes no sense to have spinners for that, since that default is computed. So stuff like the UVW actually ends up here with only a map slot, compared to the other parameters that get spinners and swatches and stuff like that, and just a tiny map slot at the end. But if I were to connect a UVW channel here, this is the shader you use to pick one channel. Now, we already were using channel 1, so nothing changed, but I have set up this scene so there's a channel 2 that is mapped differently. So this is UV channel 2. If I pick channel 3, which doesn't exist, well, nothing happens. You just get 0. So this is how you basically apply UV coordinates. And I'm going to talk a little bit more about that now, because we're going to get to the first one in our kind of generic category, which is the bitmap. Bitmap lookup in OSL is done in a couple of ways, and I'm going to show you one of them, which is this shader, the bitmap lookup. This is actually a very simple shader. We connect it here and we see that it comes preloaded with like a UV grid, and we see how this shows up on our object, as you would expect. It has some very minimal settings for things like there's a scale setting. You can say if it's going to repeat or not. If it returns black, you can have mirrored repeating as well. And you can have just standard periodic where it repeats the normal way. You have some gamma options, and that's literally it. You notice that we are not able to set the UV channel for this. There's no transform beyond this simple scale. So if you're a Max user and you're used to kind of the old Max bitmap, this might look a little weird to you. But for the channel, I already show you how to do that. And for transforms, we have a specific node called UVW transform. So if we hook these up and look at our UVW transform, you will see this has things like, yes, it has a scale. That scale scales up things when you turn it up and down when you turn it down, as you kind of would expect. There's tiling, which is for each channel X, Y, and Z. Now this is 2D, but the UV transform can deal with 3D coordinates, so it has them all. But I say 3, it tiles 3 times in the U channel, and I say 6 here, and it tiles 6 times in the V direction, for instance. Now, this is kind of a dividing scale. It becomes smaller when you add it because the mindset is tiling. But if you do things like you scale it up by 3 and you tile it by 3, well, these kind of cancel each other out, so it's not really meaningful. We have the offset, which is offset in the U direction and offset in the V direction. And if this was a 3D coordinate, we would have it in the Z direction as well. There's a rotation, which is in degrees, so 45 degrees seems to be clockwise actually. And there's a rotation center, which is now at 0.5, 0.50, and this is in UV space. So this is the 0.5 UV coordinate right there, and it will rotate around that, and it will rotate around an axis of 001, which is the Z axis, and then again this is in UV space. So for normal 2D rotations, it would be around the Z-axis like this. Now you think, okay, so I have my bitmap, which does these things. I have here's where I pick my channel, and here's where I do my transforms. But I'm kind of used to the Max way of doing things, where they're all in one. So we did prepare specifically, because this was a comment on like the beta forums, we made this one, which we call the Uber bitmap. This is literally just these 3 things thrown together. So it does exactly the same. If I connect this one instead, you will see this has a map channel. You have the scale and all this stuff. We have the bitmap. So it's literally these 3 things thrown together. So the use case for that is when you want to use it for something like similar to a Max bitmap. But the problem you get into now this is all built in. There's no way for you to go into these things in the middle and do stuff with it. Versus with this case where everything was split apart, we can say, for instance, well, we might go to the math category for vectors and add a vector add here. And then we would say we could take a 3D noise, for instance, and we could add that to our UV space. And now we made a distortion. We put stuff in the middle of the math equation, and we could now make a distorted UV coordinate for our bitmap lookup. And that gives so much more freedom to what you can do. So it's really up to you. Do I really want to use this monolithic bitmap lookup, or do I want to assemble everything? Because, for instance, these UV coordinates could be shared over 10 different bitmap lookups and all these kind of things. So it's kind of up to you, but just informing, the Uber version exists if you want the all-in-one as a single node. Let's get rid of this for the moment and say that we try some of the other one. We have the Blackbody shader, for instance. This makes a color based on a Blackbody radiation, so from 0 to 5000 Kelvin. So there's an input here where you put in a value. And again, we have a default. What's the default? It's the U channel. You can see it here. Which means that if I don't plug anything in, it will make this like a gradient across the U channel of the object. But I can plug something in here if I want to. So from 0 to 1 in this input, we go from 0 to 5000 Kelvin. So I can say, no, I'm going to want to go to 9000 Kelvin, or I want to go from 3000 Kelvin to 9000, or whatever, 1000 Kelvin. So we can decide our little Kelvin gradient. If we feed it with something slightly more interesting, let's just, for the hell of it, throw in the Mandelbrot shader here as feeding it with that. And let me tweak the output of that a little bit. Let me see, 1 second. More iterations are always good. There we go. Now we have a little fiery Mandelbrot set. That's a glow. Now, the Blackbody shader has a checkbox called normalize. Be wary about that, because that means when this is checked, it just computes the color. So it becomes a nice soft gradient. If I uncheck this, it will give you also the computed intensity based on the Blackbody. So you'll see this turns super bright. Even if I do 0.001 here, it's still kind of bright. I might need to still turn this output back down. But the point is, it now has super ultra bright intensities, but correctly computed based on the Blackbody radiation for that. Of course, for most kind of, I just want to make it pretty cases, there's probably easier to just use the normalize mode. So that's the Blackbody one, and since we already start playing with the Mandelbrot, just let's mention that. Put the values back. So this is a classic Mandelbrot shader to make our fancy little fractals. It's more kind of a programming example maybe than anything. One interesting part with it is that it's actually multidimensional. The Mandelbrot equation actually allows us to do it that way, but the default UVs are actually the standard UV channel. But I could try this. I say I want to use object space, or even better, I actually don't want to use object space. I want to use a named coordinate space. I want to use world. And then I have to tweak the scale a lot. When I use the world coordinate space, you will see our Mandelbrot actually spills out over the side here. And since we're using the 4-dimensional version or 3-dimensional version, it's not just straight lines down, but there's actually stuff happening here. If I even take this box and move it up and down, you will see that the shape of the Mandelbrot set, there's different slices of it. This is really interesting. I made a super freaky animation if you want to see what the 4-dimensional Mandelbrot set looks like. But it's a fun shader you can play with if you're a fractal nerd. Going on kinda in sequence, we have the candy. It's not really interesting. Again, it's kind of a programming example more than anything. It makes random dots in space where you can set the size. Perhaps the most esoteric feature is that it has a bump output, so you can make bumps, though it seems that you need to turn the bumpiness up quite a lot to see it. You see now it looks like somebody threw Skittles all over the thing. And actually I notice if you do this, it's more obvious. We have like blisters on our thing right now. This alone might be maybe useful for something. Checker we already kind of did. We have composite. Composite just puts one texture over the other. And right now, of course, we have nothing. So let's plug in a checker at the bottom layer. Bottom layer RGB is our checker map. And then you see nothing happens because the top layer's alpha is full. So if it's 0, we only see the bottom layer. And if it's 1, we only see the top layer. And everything in between there is a fade, as you would expect. If we try then to do that with a bitmap, and we load the one in which has an alpha channel, so we connect the color. And in OSL, alphas are separate, so we need to connect that. And now you see we have our Yoda composited on top of our checkerboard. Maybe not the most elegant example in the world, but you get the idea. Want to composite multiple layers on each other, you can just cascade them into each other and do pretty much anything with that. Very powerful. Digits is a fun little shader that you can use for debugging purposes and other fun stuff. It shows you a number. I can put in any number here and it shows this number, and you wonder, why would I ever want to use this? Well, take for instance the example that we want to play around with per object settings, which is something we do which taking the scene attribute called node handle. What if I take the node handle and put it in the number input? Well, what do you know? It will show me the node handle of each object. So this is number 1. This guy is number 2. And for reasons of how I built the scene, this happens to be number 15. So those node handles can then be useful. We can, for instance, derailing a little from our main category here, pick something like from the color there is a index-based randomizer. Let's see now, where is it? There we go, random by index. I connect the index number here and connect the output to, we can use it as the background color of our digits, like this. And then we say this goes from ugly color like this to an even uglier color like this. So it will be an interpolation between these two colors based on randomness. The randomness can of course have a seed where I pick different seeds and the randomness is different. I should really pick a worse set of colors so it's more obvious, like this. And this is now per object. So if I were to copy this teapot, 10 times, I'll get 10 different colors like that. And since I piped it through the digits, I can actually see the node ID on each of them, 18, 19, 20, etc. So another way to do that, while we're derailed off the main category, sorry about that, we have this category called switchers, where we can use this one called 1 of 10 colors. So instead of using this thing, I will use the 1 of 10 colors as the background of my digits and drop this index in. And you will see all this is black. Why are all these black? Well, the 1 of 10 colors has a color for 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then it has an outside range output. So if I make this purple, we see everything that was outside that range becomes purple. Or I can say the start index will be at 10. Now you see it works there. Or even if I say 15, it will have these colors starting on index 15. Or I can simply say I wanted to use just these first 6 colors. That means it will cycle through, so it will pick them like this, and then take them again. So now suddenly I have different colors for all of these things, and they are picked based on the node ID. So that's one of the things you can do with that. I feel a little derailed from my original thing about the main category, so let's get back to that. But hey, we're having fun here. Lift gamma gain is a fairly trivial color correction shader, which if you look at the source code you kind of understand. It takes the lift, it adds the lift, it raises the input to power of gamma and multiply by gain. So the order operation is take the input color, raise it to the power of gamma, then multiply it by gain and add lift to it because of the order of operations. So if we look at what that does, adding lift makes everything brighter. If we make it negative, we can make some nasty effects where we subtract values, although I don't recommend negative values. Gamma will tweak the gamma of these colors, making them more saturated or less saturated. And gain will simply multiply it. And then you think, well, maybe the same feature in some other tool uses another order of operations. Well, you can fix it. I say, actually, I want to do... Oh yeah, I have to unlink it. There we go. I say, actually, I want to apply the lift before the power function. Like that. So now you get a slightly different behavior if that's what you like. This is the simplest possible color correction shader we have in here. The Mandelbrot we kind of did. Noise is like the simplest version of noise. It is a one-dimensional one. I'm talking a one-dimensional for the output. So if we zoom in here, we see it's basically a floating point output noise. It has some modes where you can pick the noise kinds. It's Perlin or unsigned Perlin, cell noise, hash noise, simplex, and Gabor noise. We will not go super deep into those details. It can do multiple octaves, so 1, 2, 3, 4. The lacunarity is how the frequency increases for each octave, which is normally 2, and gain is how the intensity is multiplied for each of the octaves, so you can actually control that. There's a step function which is similar to the step function in the max noise, but it is applied per octave, which is quite different in its look and behavior than what is done in the max. Because if you want to put the step function outside of the noise, you can just apply a step function here on the wire, but this one is in the middle of the loop of the octaves. There's an amplitude, there's a phase, and stuff like that. Now the phase, of course, randomizes the noise, and you can use that for changing over time, but you can do something more interesting with that also, because if you were to hook up the node handle we had way over here and connect that to the phase, you see we effectively get a setting for one noise per object. You see the teapots no longer have the same exact noise on them. If I disconnect that, oops, you will see that all the teapots are exactly the same, which is boring. With this connected, you have basically a randomization of the noise. We have this other noise called 3D. Now don't misunderstand this as being because obviously this is 3D for the input. It's the output side we're actually talking about here. And interestingly, for the same set of inputs and the same set of settings, this noise red output or first output is actually completely identical to this noise. So the only reason this kind of one channel noise exists is an optimization. It does less math basically, and it's slightly faster, although it's probably negligible. Here we have the one which has 3 output, X, Y, and Z, or you can treat it as a color or a vector, which mostly now looks like, freaky color noise. But if you do stuff like, distorting 3D coordinates with it or something, that's when you want to use the vector output. Another interesting type of noise is cell noise, which is useful for some cases. Cell noise means that within a given unit cell, and it's more obvious if I used only one octave, there's one value. So if you want to move things randomly, you often use the cell noise, so that within each square the noise, one by one square, the noise keeps that value, and when it gets into the next one by one square, it changes the value. Or one by one, I mean, it has to do with the scale, obviously, the size of these. But cell noise is used for a lot of effects. We will talk more about cell noise when we get into writing shader, because it will be one of the most useful noises in that case. The Gabor noise is a special noise algorithm. It's not so much that the look is any different if we have similar settings, but the difference is that it's computed in a different way, which is supposed to be more smooth and filter better. It actually has lower performance, so it's kind of a toss-up which you want to use. I kind of never use the Gabor noise myself, and actually you can use that as one of the modes of the regular noise, so whichever. Now we come to the randomized bitmaps. This thing does so much that I plan to make a whole video only about that. So I'm not really saying much more about that right now. And the same is kind of true for rivets, our steampunk shader, which I think I showed in the overview video. It's kind of cool. It looks kind of nice, and it can do a bunch of stuff, but I'm kind of leaving that for a video of its own, which kind of leaves us finally here in the main category with the wavelength shader. And the wavelength shader is kind of the same as the, remember in the beginning we have the Blackbody. It has an input, and this goes from two different wavelengths, from 400 to 700, and gives us that rainbow look, exactly like the Blackbody one. It has a default input, which is just the U channel, but of course we might want to drive it from something more interesting, like say let's drive the input from this noise here, and we get some interesting color effects based on that. So that's the super quick view of the main category. Now if we try to look at the subcategories and see what they do, I do not plan to go into complete detail for everything, because some of this stuff is pretty obvious. Like we have a math color category, which has adding colors, clamping colors between two values, so a min and a max. Components basically takes a color and breaks it into components, or assembles the colors from components. So you can just plunge in a red here, or put a complete color in here and get the red, green and blue out, etc. Divide will divide color. Interpolate will just interpolate color based on some input. So it will go from you know, you say I go from red to, you know, green. Not very advanced. Depending on this value, you can see the output here changing. So now it's green, now it's red, and of course if we drive it from something, then invert will invert the color. Max will take the maximum per component value of two colors. Minimum. Multiply will surprise multiply. Random by index I already showed. You put in an index and a random seed, it will randomize between those color values. Smooth step is an effect, or a basic feature in many shading languages, where you have an input and then you have a low and a high threshold, and when you're below the low threshold it will return black, when you're above the high threshold it will return white, and near these thresholds there will be like a smooth curve, so it doesn't just smack go top to bottom in a simple linear, it kind of makes a nice smooth S-curve. So when you want to do steps of something, smooth step is always nice. Subtracts, and tweak is actually a kind of cool color correction shader. Actually, to show off tweak, I'm going to move a bunch of crap here we're not using and put in a bitmap. bear with me for a second. So I'm going to take a picture here and drop it through the tweak shader, and we can see a little bit what it does. We see we have this beautiful little color chart kind of image that we're going to play with, and I'm actually going to move it down because one interesting part is these grayscales up top, which is going to be important. Tweak has a low and high input value. This works very much like levels in Photoshop, and a low and high output value. So if I raise the low input, it will actually be like a black crush. We see all these dark squares become dark. Or if I lower the high input, we see we're pushing the light level up, so all these become white now instead of having the grayscale. Similarly for the output side, if we raise that, we see we're all gray because we put like a pedestal onto it. And if we lower the output side, obviously it just gets darker. But the true interesting thing, if we start putting colors in here, so let's say we make this kind of blue on the low side, and we make this kind of orangey on this side. So now we made kind of an old-timey photo look kind of thing, or looks almost like an Instagram filter or whatever. We have hue shifts where you can tweak the hue, we can tweak the saturation. Doesn't work so well if you overdrive it, and the value, which is of course the same as a multiplier. It's not very useful. So this can make some kind of cool color tweaks, and be kind of used as a color correction shader for that kind of stuff. Go back to our list of things for color. Yeah, we're done with color. Floating point. Well, it's basically every mathematical function: absolute value, arc, cosine, add, angle, arc sine, arc tangents, clamping values, complement like 1 minus, cosine, degree to radian conversion, divide, exponent, convert a float to an integer, interpolation, logarithmic base x, maximum minimum, modulo, multiply, negate, power, radians to degrees, random by index again. Range remapper is kind of interesting. It's kind of almost like the color tweak but for floats. Basically you have a start and end range for the input, and you have a start and end range for the output, and you have a remapping curve in the middle. So if you know you have some input that goes from 1 to 7, and for whatever reason you want this to map to an output that goes from 1.0 to 0.7, you just say okay, 1.7 is the input, and 1 and 0.7 is the output, and it just remaps it for you. It's kind of useful. Sine, the smooth step again, square root, subtract, tangents. For vectors, also math, add them, get the components, exactly the same as we did for the colors. You can pick it apart in XYZ or put them together. Cross product, distance, divide, dot product. We're gonna get more to that. We start write shaders and understand what cross products and dot products are. So I will kind of leave that as the next. Invert them, like flip them, check the length, maximum, minimum, multiply, normalize vectors, basically make their length 1, which is super useful in computer graphics. There's random by index here as well, and subtraction. Scene data. Now this is fun. Scene data can get stuff from the scene, like the frame number, which is obviously kind of obvious as it's the frame number. You also have the time in seconds, which you can feed stuff to shaders you want to animate. Of course, you can animate the values, but if you want to make something that happens kind of automatically, you can, put the frame number in. Like you can even do this if it amuses you. Connect the frame number to the digits shader, and you will find that it updates to the current frame. Material ID will return the material ID of the object. Hardly surprising. It can do it as both a color, which is using kind of the way that Max normally shows colors. You see boxes in Max have different material IDs on different sides, or as an index number, so you can drive like a randomizer with it. Node handle I was showing before. I'm skipping named attribute intentionally. Node handle I showed before. It's basically the integer index of the object in the scene, which we used before. Node name and its hash can be useful. So node name will actually return the name of the object as a string. So this input is actually string output. Now we don't have much that accepts string inputs. There's actually on the GitHub a dot matrix that can print them, but there's cases where this can be useful. But it's also a hash value, and this is a hash value of the name, and that can also be useful to drive random stuff. And the cool thing now, since this is based on the name, if you name 3 things the same thing, like 3 teapots gets named Bob, they will have the same hash, so they will have the same random result. If that is useful to you in some way, you can do it. Object ID is the object ID in the scene as defined by this. Right click, object properties, object ID. There. And please note one important thing. You see it did not update. This is kind of an old deficiency of Max, that object properties are not properly handled in the notifications. So you see I had, for the first time on this entire demo, I had to restart my active shade. But now you see this has object ID 3. And if I change this to have object ID, something else, 5, yeah, I have to re-trigger the rendering, and then it works. Very good to me. Particle age, if you have a particle system, it will be the age of the particle. You also have the wireframe color, which you can use, and especially you can use the RGB values of the wireframe color to drive things, which can be kind of interesting. Now these are all the same wireframe colors, and make this ugly like this. Same problem, restarting active shade. Apologies, but it's a very deep misfeature of Max that doesn't work. So that's wireframe. Now let's get back to those named attributes that I skipped earlier. So what is that? Well, you can get a bunch of named attributes, and actually if we open up this shader like the wire color, you'll see the only thing that actually does is get attribute wire color. So let's try this. Let's take this one instead. We connect the color here, and we see we get nothing. But if I say, oh, I wanna use wire color, and now we're doing exactly the same thing as the wire color shader. Actually, we are getting the wire color attribute. And that happens when this is not checked, because then it will ask for the attribute that is exactly as written here. However, there's another fun thing you can do, and it's this. Let's right click this object, go to user define, and say color is 100, and we right click this one and say color equals 110. Okay, and then again the problem, object properties are not updated unless I do that. And then of course I say color here. You see nothing happens. Why? Because I need to check this one, user defined property. Now this is, of course, was silly. The default I set that to blue. We'll see that anything that didn't have the color property is now blue. Those that did have the color property return this one. It was red and yellow. This works for color values, for floating point values, integer values, and even strings. So you could have stuff like file names for textures attached to objects if you want. So say test is 0.2 as an example, and we say that we put in a new named attribute here and say test and set the float default to 1, and we take the float output and set that to the base weight map. We should see, oh, I need to restart it again sadly, this one, it will have its color turned down because it will not get 1, it will get the 0.2 value that I put in. Very powerful stuff. You can do all sorts of things with that. Then we get to the switchers category, and I kind of showed this earlier a little bit. We have this 1 of 10, and we have a 1 of 5. It's difficult in OSL to make something with a dynamic number of inputs. We haven't really solved that yet, so for that reason we have this 1 of 5 kind of things. And there's a way to cascade them into each other. As you recall, there was an outside range here, and I can set the start index. So what I can do is that if I have one set with the start index of 0, and then I have a second one which I plug in to that one's outside range and set its start index to 5, they will then cascade together, so you have from 0 to 10 or 0 to 9, the first 10. Of course we already have for 10, so that's not a good example, but if you want to do 62 of them, you can do it by cascading, together 6 10s and a 5, for instance. There's a compare, which basically compares, you have an input A and B. If A less than B, it returns this color. If A is equal to B within this equality threshold, it uses this one. If A is greater than B, it uses that one. You can use this to trigger all sorts of things. And there's a simpler greater than, which has an A and a B, and if A is greater than B, it returns this one. So, and if it's not, it returns the other one. You can have that to drive other things and do a lot of stuff. The UVW category has this one, which gives a named coordinate space, and as you can see, it has object by default. You have world coordinates, you have the screen coordinates, you have NDC non-device specific coordinates, I think it stands for, which is kind of a version of screen, and raster is in pixels with 0 0 up here, so it will actually count pixels. If you for whatever reason would want to map something to pixels, that's the coordinate space you get. You have the UVW channel, I kind of show that. UVW environment makes an environment mapping, and you have the choice of spherical and mirror ball. Might get extended in the future. Object space is kind of a shortcut because you use it so much that it's just a shortcut to get the object space. It doesn't have any parameters. It's actually exactly the same functionality that's taking this one and choosing object. It's kind of redundant, but it's kind of more obvious when you see it in the scene that, oh, I have an object space here, because you can see it in the name. Here it's like, oh, some coordinate space, I don't know which one. The row offset, the transform I showed in the beginning, the row offset, I will probably show that more when we do the rivets thing, but it's basically a thing that takes rows in UV space and offsets them for things like bricklaying and stuff like that. Finally, the UVW transform, which we kind of did. And then we have values. Values are straight pass-through of each of the types. So this is a color which has an input and an output color, which just passes it straight through. You can use it for a couple of things. If you just want to send the same color to 10 places, I for whatever reason want to connect this, color over here and color over there, whatever, and I want it in one place, so I can edit it in one place, you can drive these things with a single color. Another use case for it is for shaders that have multiple outputs, and you just actually want to look at the output, because what you see, let's take an example. Let's take the Mandelbrot has more than one output. What you see here in this little preview is always what's in the first output. If you're curious what's in the second output, you can just do this and see, oh, it's kind of the alpha channel of the Mandelbrot. So So now we know. We can use it as kind of a viewer. And of course now we have split that up to go to those two places as well. So these are all just kind of pass-through things for colors, file names, floats, integers, strings, and vectors. And then we have a final interesting one, which is a numbered file name. It takes a base file name and the frame number, and then builds this file name which adds before the extension these so 0000 if it's in this particular case, and we say it always does 4 digits, I think. And there is a mode where it says replace, then your incoming file name already have 4 digits and it will overwrite them. If it doesn't say replace, it's assuming the file name looks like this, and it adds in the 4 digits here. Can be useful for animated textures and all sorts of fun stuff. Finally, you see I have a thing here called ADN Experimental. Those are actually shaders coming from the GitHub thing, and we're going to talk about that in a different video. But this was kind of the super fast walkthrough of all the OSL shaders shipping with Max 2019. I hope you enjoyed.